Welcome to Chapter 8, Information Theory. How much does a message actually say? Some messages tell you almost nothing, others tell you a great deal. In this chapter, you will measure information in bits and find the true limits of how far you can compress data and how fast you can communicate. Think about two messages. The sun rose this morning tells you almost nothing because you already knew it would. A meteor struck downtown tells you a great deal. Both are short sentences, but they carry wildly different amounts of information. In 1948, Claude Shannon made that intuition exact. Information is surprise. It is the resolution of uncertainty. A message you were certain of carries zero information. In this chapter, we measure information in bits, and we find the true limits of how far you can compress data and how fast you can communicate. Let's look at the plan for this video. It has 4 parts. First, self-information. How much one event surprises you, measured as the log base 2 of 1 over its probability. Second, entropy, the centerpiece, the average surprise of a whole source. Third, source coding, where entropy turns out to be the floor on how few bits per symbol any lossless code can use on average. And fourth, channels and capacity, the fastest rate at which you can send data reliably through noise. We begin with a single event. How much information do you gain when you learn it happened? The surprise of an event is called its self-information, and it depends only on the event's probability. The formula is information equals log base 2 of 1 over p, drawn here as one line. At probability 1, a certain event, the surprise is 0 bits because you learned nothing. At probability 1/2, a fair coin flip, the surprise is exactly 1 bit. As the probability shrinks, the curve climbs. Rarer events carry more bits of information. Let us put numbers on the curve. A fair coin has probability 1/2. Its surprise is log base 2 of 1 over 1/2, which is log base 2 of 2, which is 1 bit. That is one yes or no question. One outcome out of 8 equally likely ones has probability 0.125. Its surprise is log base 2 of 8, which is 3 bits, because 8 is 2 times 2 times 2. Each halving of the probability adds exactly 1 bit. And a 1 in 20 event has probability 0.05. Its surprise is log base 2 of 20, which is about 4.3 bits. The rarer the event, the more bits it delivers. Read the curve one more time. A common event carries a little information, and the curve climbs steeply as the probability approaches 0. A certain event carries no information because you already knew the answer. A rare event carries a lot. One more property matters. If 2 events are independent, their information adds. The surprise of both together is the surprise of one plus the surprise of the other. That works because the log of a product at times b is log a plus log b. This is exactly why Shannon chose the logarithm. A single event has a surprise, but a real source, like a weather station or a text file, produces many events. To describe the source itself, we average the surprise. Entropy is the average surprise of a source. Written H, the formula is H equals minus the sum of p times log base 2 of p, taken over every outcome. Each term is one outcome's probability times its own surprise, and we add them up. Look at the hump for a single coin. When the coin always lands the same way, at probability 0, the entropy is 0. There is no uncertainty. At probability 1, it is 0 again for the same reason. The result is certain. The entropy peaks at 1 bit when the coin is fair, at probability 1/2, because that is when you are most uncertain about the next flip. Now a concrete source. A weather station reports one of 3 outcomes each morning: sunny, cloudy, or rainy. First, we find each outcome's own surprise. Sunny has probability 0.7, so its surprise is log₂ of 1 over 0.7, which is 0.515 bits. Sunny is common, so it barely surprises you. Cloudy has probability 0.2, giving 2.322 bits. Rainy has probability 0.1, giving 3.322 bits. Rainy is rare, so each rainy day carries the most information. Now we average. Entropy weights each outcome surprise by how often that outcome happens. The sunny term is 0.7 times 0.515, which is 0.360. The running sum so far is 0.360. The cloudy term is 0.2 times 2.322, which is 0.464. The running sum climbs to 0.824. The rainy term is 0.1 times 3.322, which is 0.332. The rounded running sum reaches 1.156. So the entropy of this weather source is about 1.157 bits per symbol. That is how much uncertainty each morning's report resolves, on average. Compare 2 coins on the hump. A fair coin at probability 1/2 sits at the very peak. Its entropy is 1 bit, the most uncertainty a single coin can have. A biased coin that lands heads 90% of the time, at probability 0.9, drops to 0.469 bits, because its result is much easier to guess. The rule holds for a fixed number of outcomes. With the alphabet size fixed, a source is most uncertain and has the most entropy when its outcomes are equally likely. A source with a certain outcome has no entropy at all. Entropy is not just a description of a source. It is a hard limit on how far you can compress it on average. Take our weather source, written as A with probability 0.7, B with 0.2, and C with 0.1. Its entropy is 1.157 bits per symbol, drawn here as the teal dashed floor. A fixed-length code, giving every symbol the same number of bits, uses 2.0 bits per symbol. Huffman coding does much better, at 1.3 bits per symbol. But it still sits a gap of 0.14 bits above the floor, and no lossless code can average below the floor. That shaded zone is out of reach for the long-run average. This is Shannon's source coding theorem, and it is worth stating precisely. First, no lossless code can average fewer than h bits per symbol. Notice the word average. The bound is about the long-run average over the whole source, not about one particular message. Second, the floor is achievable. For any small margin you choose, there is a code whose average length comes within h plus that margin, if you are willing to code longer and longer blocks. Third, a single lucky short message might, by chance, use fewer than h bits per symbol, but no code can beat h bits per symbol on average over the whole source. Entropy is the wall. Compression asks how few bits you need. Now the other side of the story. Those bits must survive a noisy channel. This is the simplest model of a noisy channel, called the binary symmetric channel. You send a bit, either a 0 or a 1. With probability 1 minus p, it arrives correct. With probability p, noise flips it to the other value. It is called symmetric because the flip probability p is the same whether you sent a 0 or a 1. That single number p captures everything about the channel's noise. Noise does something subtle to information. Noise makes each received bit less certain. When a bit arrives, you cannot be sure it was not flipped along the way, and that uncertainty is what limits how much information gets through. Shannon defined the channel capacity as the highest rate at which you can still communicate reliably, meaning with an error rate as small as you like. This is a limit on the reliable rate, not on raw speed. Below capacity and with long enough codes, a good code can drive the error rate as close to 0 as you want. And the way you buy that reliability is exactly the redundancy from Chapter 7, the extra bits of parity, hamming, and CRC. Let us gather what this chapter gave you. 4 takeaways from this chapter. First, self-information measures surprise. The information of an event is log base 2 of 1 over its probability. A certain event carries 0 bits. A rare event carries many. Second, entropy is the average surprise of a source, minus the sum of p times log base 2 of p for the source 0.7, 0.2, 0.1. The entropy is 1.157 bits per symbol, and a fair coin is exactly 1 bit. Third, source coding. Entropy is the floor. No lossless code can average below h bits per symbol, though you can get arbitrarily close in the limit. Fourth, channel capacity is the fastest rate at which you can communicate reliably through noise, and redundancy is what buys that reliability. That is Chapter 8. You can now measure the information of a single event as log base 2 of 1 over its probability, compute the entropy of a source, red entropy, as the floor on the average bits per symbol, and explain channel capacity as the limit on reliable communication. Chapter 9 is the capstone. You will build a binary toolkit that ties every chapter together. Number conversion, UTF-8 in Huffman coding, CRC, and the entropy you just learned all in one working program. See you there.